Hello everyone, this is Syed Afif from section of AML. Today my topic is Q and from the subject of design and analysis of algorithms. So I want to start with what is Q. So here Q is a linear data structure that follows the first in first FIFO principle. Elements are added at one end called the rear and removed from the other end called a front. Think of it is like a line of people waiting for a bus. The first person in the line is to board. Queues support two primary operations, enqueue insert and dequeue that is remove. They are widely used in scenarios requiring ordered processing such as task scheduling or the bed first search. And we will see the core operations of queue, that is enqueue adds an element to a layer of the queue, increase its size by 1. And the next one is dequeue removes and returns the element at the front, decreasing the size of 1. And the front or the peak that is returns the front element without removing it, useful for inspection. Is empty, checks whether the queue contains an element or returning true or false. And the last one is full, is relevant in bounded queries or the queues to prevent overflow when capacity is reached. So next one is queue implementation, array based. So here an array based queue is used a fixed size array to store elements sequentially. Two indices, front and rear, track the positions for dequeue and enqueue operations. When rear reach the end, the queue may appear full even if space exists at the front due to prior dequeues. Next one is this issue is solved using a circular array, where indices wrap around using modular architecture. Circular queues efficiently reuse space and maintain time complexity for core operations. The queue implementation with a linked list based. So a linked list implementation uses dynamic memory allocation with nodes containing the data and a pointer to the next node. The next front pointer to the first node and the rear pointer points to the last node for efficient enqueuing. Enqueue adds a new node at the rear and updates the rear pointer. Dequeue removes the front node and updates the front pointer, freeing memory if needed. This approach avoids size limitations and supports flexibility growth and ideal for dynamic workloads. So time complexity of queue operations, both enqueue and dequeue operations takes constant time, that is O of 1 in well implemented queues. Front and empty operations also run in O of 1 time as they involve simple pointer or index checks. In array-based queues, circular buffering ensures O of 1 performance without data shifting, and linked list implementations achieve O of 1 by maintaining direct access to both ends. Overall, queues are highly essential for insertion and deletion at opposite ends. So next one is bounded versus unbounded queues. That is, a bounded queue has a fixed maximum capacity, often implemented using arrays. Attempting to ensure into a full bounded queues results in an overflow error or blocking behavior. A unbounded queue can grow dynamically, typically using linked list or resizable arrays. Unbounded queues avoid overflow but may consume excessive memory under heavy load. Choosing between them depends on system constraints like memory availability or predictability needs. So a priority queue, that is next one is a priority queue and extension of queue. A priority queue assigns a priority value to each element, determining the order of removal. Unlike standard queues, elements with higher priority are dequeued before lower priority ones, regardless of insertion order. Common implementations use heaps, especially binary heaps, for efficient operations. Insertion and deletion in a binary heap-based priority queue take off log n time. Priority queues are essential in algorithms like Dijkstra's shortest path and job scheduling systems. DQ, double-ended queues. A dequeue allows insertion and removal of elements from both the front and the rear. It combines feature of stacks and queues, offering greater flexibility in data. Operations include add front, add rear, remove front, and the remove rear, all typically O of one with proper implementation. And the DQ can be implemented using dynamic arrays or doubly linked lists. They are useful in sliding window algorithms, palindrome checking, and undo, redo functionalities in software. So here the real world applications of queues, that is operating systems OS use queues to manage processes in the ready queue for CPU scheduling. Network routers employ pocket queues to buffer incoming data before transmission. Print spoolers maintain a queue of documents waiting to be printed in order. Web servers use request queues to handle incoming client connections fairly. BFS, that is breadth first search in graphs, relies on queues to explore nodes level by level. And the queues in AI and ML, that is machine learning, in reinforcement learning, experience replay buffer use queues to store past state action reward tuples. And this buffer enables agents to learn from historical data, improving training stability, that is from the past data. And message queues facilitate communication between distributed components in ML pipelines. Task queues manage asynchronous model training jobs in cloud-based AI. Queues help decouple data producers, example sensors from consumers, example inference engines in real-time systems. Common queue related problems, that is queue overflow occurs when trying to enqueue into a full bounded queue. Underflow happens when attempting to dequeue from an empty queue, often causing runtime errors. In multi-threaded environments, race conditions may arise if queues are not thread safe. Solutions include using synchronized queues or concurrent data structures like concurrent linked queue. Proper error handling and capacity planning are essential to build robust queue-based systems. Analyzing queue performance. Performance is measured by complexity of operations and space utilization. Array-based queues have of one operations but fixed size, limiting scalability. Linked list queues offer dynamic seizing with O of one operations but use extra money for pointers. Circular arrays optimize space reuse and ideal for embedded or memory constrained systems. Choice of implementation depends on application requirements like speed, memory, and concurrency. The next one is best practices and design considerations. Always check for empty or full conditions before dequeuing or enqueuing to avoid errors. Use thread safe implementations. when queues are shared across multiple threads or processes. Prefer circular array for fixed size scenarios to maximize memory efficiency. Monitor queue length in real-time systems to prevent latency spikes or resource exhaustion. Document whether your queue is bounded or unbounded to guide proper usage in larger systems. So thank you for giving me opportunity to explain the basic concept of queues.